Hi! Welcome today for another episode of This Is Your Homework. Thank you for joining me for lesson 46. Simplifying expressions with square roots and higher ordered roots. Haha! Ain't that fun? 46. There we are. I love numbers. I even wear numbers on my shirt because they're so fun. Hey, today I do want to talk to you about getting to know numbers better. There was an Indian mathematician, Ramanujan. We made a movie about him recently, and it was said of him that that the integers were some of his best friends. When a guy came and visited him in the hospital, I mentioned to him that he had ridden in a taxi cab number 1729. Ramanujan says, "Oh, isn't that interesting?" And he gave like 3 different properties of that number. It was the only first number that could be, divided up in 8 different ways and whatnot. Anyway, we are going to talk a little bit about your number sense today and maybe how to develop that a little bit. You probably will want your handy-dandy notebook to put a few extra things in the back for some resources for yourself today. And again, lesson 46, that's where we're going with this. You can have your calculator out, but you're only going to need that to double check on some things. And I will get mine out and show you where some of the buttons are for you to push. Let me push a button right now and get my own calculator out before I keep going. Okay, got one of my best friends here with me here today. I'll leave that right there for later. Okay. So, what are we talking about today? Well, we're going to talk about operations. We're going to talk about operations and opposite or inverse operations really quickly here. And we've got our basic operations, subtraction and addition, which are obviously opposites of each other. If you add A and subtract A, you get back to where you started from. We also have multiplication and division. Same thing, if you've got a number, let's say it's 5 and you multiply it by 4 and then you divide by 4, you get back to where you started from. Or even if I had 5 and divided it by 4 and then multiplied it by 4, I get back to 5. That's their inverse operations. They will undo each other. And we've been doing this for a while with equations where we do the same thing to both sides. If it was added 5 on one side, we're going to subtract 5 to both sides. We know how that works. Well, today we're going to talk about powers and roots. Okay, powers, when you're going to take some number and you're going to multiply it multiple times. So powers are very similar to multiplication. And then let's just take the squared power, and then the opposite of that would be taking something's square root. That is finding a number that if you had multiplied it by itself would equal the number underneath the radical sign. So for instance, if we had the number 36, we'd be looking for a number that, well, it's a square number, right? So if we had the square root of 36, we could write that as 6 squared square root. And then those two things will cancel each other out. It'd be like saying 6 times 6 divided by 6 and going back down from there. But we do it up here in the powers to simplify things and make it so that we're only dealing with like a small problem. But we need to like wrap our brains around the way that looks. Now, one thing to tell you is that you rarely ever see anybody write one of these radical signs with a 2 out in front. And that's because if it's missing, it is understood that something's being taken to the second root, or what we call the square root. You think about this. When we do this, we call that squaring. And we can think of it in terms of area. We'll take something that's n units long, we multiply by something else that's n units long, we get a square. So basically what we're doing when we take square roots is we're saying we have this area, and what would be the side of that square. That's the way that the Greeks would have thought about square roots. They would be thinking about it in terms of shapes, right? Squares. So to take a square root is basically to take something from 2 dimensions down to just 1. Squaring takes things that are in 1 dimension and bumps them up into 2. That's going to come in handy as we talk about higher orders of things today. But I want you to first get that stuck in your mind that squares and square roots are inverses of each other. And that's going to follow that cubes, taking something times itself 3 times, and cubed roots are opposites of each other. And I think you'll see that when we give you the other kind of notation for these types of rules. So if you had something like this, we're asking for what number times itself would equal 64. We could write this as, if we know our numbers well enough, we would know that 64 is a square number, that it's 8 squared. And again, it's understood, if there's no number there, that's understood to be the principal root, is what it's called, like the first one that you would do. There's an understood 2 there, and those 2 things will cancel each other out. So if you take the square of something and you square root it, you just have that number. Well, there's lots of these that we can do. We can even throw in negatives in there, but only outside. If we had negative square root of 9, that negative is like -1 times whatever is underneath the root sign there, the radical or the radicand. And you'd still have that negative hanging out there, and then you'd solve the problem inside of here. And I'm going to do it kind of clunky way here. That 9 is 3 squared, and 3 squared, square root of 3 squared is just 3. That negative follows along and stays with the problem. So you're going to have those. Some of them you may not believe, but you're going to want to double check on your calculator. But this one right here does have a definition. The square root of 0 is 0. You can even do it with fractions. You can have the square root of, let's make it 9 over 25. And the rule for these is that you can take the square root of the numerator and the square root of the denominator separately. Both of these are perfect squares. But we are allowed to break this up into smaller problems, which is a really good mode for going about attacking a problem, is to break it up into simpler pieces. And we keep the numerator in the numerator. We keep the denominator in the denominator. And if you want to double check that, you could take 3/5 times 3/5, and you'll get 9/25. One thing that we can't do, though, at least we can't do it yet with the real number system, is to have something like a negative under a regular square root. Now, there is no number that if we multiplied it by itself would equal -49. We already know that you need 2 negatives to make positive. And you need a negative and a positive to make a negative if you're doing multiplication. So if you're doing the same thing twice, you'd either get plus plus or minus minus. You would never get this type of thing here. If you try this on your calculator and it's in the regular mode, the real number mode, it will say something like non-real answer. Now, there's a way to trick your calculator into doing that, but if you check your mode down here under sequence, if it's in that first one where it says real, then that's the type of answer this thing will give you. If you want to do square roots, you're going to use your blue second button, and then you're going to push the x squared, because in blue above it you've got a little root sign there. So that's what you need to do in order to carry out that operation. So let's try it to go negative. That's this one down here, not the subtraction sign, but the negative sign. -49, and for right now it says error, non-real answer. So I'm going to trick it. I'm going to go into my mode. I'm going to change it really quickly just because that's the way I keep it. I'm going to go to the A plus BI mode there. It's called having it in a complex form. And now if I bring up the exact same problem, it actually does give me an answer. But it's got a letter there. It says 7i. That's kind of confusing. For now, just keep your mode in real mode so that you know if something went wrong. Okay? That's a good way to treat these problems. Now, I did talk about there being higher orders, higher than just squared. We got squares and cubes in the 4th power and the 5th power, and then we have 4th roots and 5th roots. We're looking for a number that multiplied by itself 5 times. Might be something that you're looking for. So this one here is called the cubed root, and it's the inverse of something that's been cubed. And think about that in terms of geometry. That's a square, and this 3-dimensional object here, that's a cube. So we would be saying, well, we got a volume, but we want to break it down to how long a side was when we take a cubed root. So if we took the cubed root of 27, now this is where your number sense has to kick in. You have to think 27 is, well, it's 9 times 3, but 9 is 3 times 3. So what we're looking at is 3 times 3 times 3. 3 cubed is 27. And the cubed root of 3 cubed is just 3. So there's some of these that I want you to kind of just get a feel for. I want you to get a feel for recognizing something like 27 as being a cube type of number. It's actually called a perfect cube. And let me give you some suggestions here. 4, 5, 6, 7, 8, 9, and 10. I think for the 2s, you should know like up to probably 2 to the 10. If you've ever played that game, 2048, it goes by powers of 2. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. If you notice over here in the corner, I've been listing the lesson numbers in binary, which goes by powers of 2. You should know those, and you should, in the back of your notebook, you should write down a list of these things. I have one kind of right here where I put in there 2 to the 1st power, 2 to the 2nd power, 3rd, 4th, 5th, all the way down to 2 to the 10th power. Okay, 2 to the 10th power is 1024, so 2 to the 11th is 2048. You should have those listed down. And you're allowed to use those, but you're going to want to be able to recognize them. Okay? For cubes, you should probably go to at least 3 to the 5th and have in your notebook what that is equal to. 3 to the 5th is 243. You can even go 2 to the 6th, 729. Those numbers come up very often in the books. And then everything here, 4, 5, 6, 7, 8, 9, you can probably go down as far as knowing what they are cubed. And then the 10s, which you can barely see off the edge of the thing, the 10s are easy. You're just counting the number of zeros in the number, and then that'll be 10 to whatever that power is. So if it's a 1 with 7 zeros after it, that would be 10 to the 7th power. Those ones would be pretty easy to pick out. There's some nice patterns in those numbers as you go down. 5s always end with 5s. Powers of 4 either end in 6 or 4. Things like that you'll pick up on the more you just look at numbers and are used to thinking about them. Last thing that I want to share with you is an additional notation for these things. Instead of writing everything with a radical sign, we're actually allowed to write these things in another way that makes them more useful, I think, and that would be using what's called a fractional exponent. That is that if this is to the 1 power here, then we could also write this as x to the 1/3 power. Okay, so if you're typing in 8 to the 1/3 power, you want to type it in, you could do 8, and then you use this caret button here, 8 to the power of, and then you can go 1/3, and it'll give you the answer 2, which is the right answer. The cubed root of 8 is 1. Of 8 is 2. Let me generalize that. Square root would be to the 1/2 power, and then basically after that we're looking at whatever the power is on that number over the root. You can always write your answers. You can always rewrite your problem like that. I think I'm going to need about 10 more seconds, so let me add another video